and in today's webinar, we're going to get an in-depth look at a piece of software called SimCenter Innovus, which is used in our end-of-line testing products here at Siemens. So this end-of-line testing product will measure noise and vibration on products coming off an assembly line and can tell you if there's defects or not. And today's presenter is going to be Olaf Strama. He's presenting from Germany. How are you doing, Olaf?
Oh, I'm fine.
So I'll let you get started there, Olaf.
Okay, thank you very much. Today it's a kind of practical webinar. I have the Innovus software running on my PC. Only for an introduction, I have some slides to show you what I will show you today. After a short introduction of our portfolio, of our measurement technique, of our solution, I will give some information about the general layout of our test system. I will show you how the hardware and the software is connected to each other. The main two parts are at first how to set up the test program with SimCenter Innovus. So assuming you have a new task on the end-of-line test to do a certain quality check of a certain item, and the first part shows how to set up the Innovus system, especially the Innovus software, in a way that it will fulfill the task of testing the items. And the second part is the analysis of data to optimize the test program. The assumption is that the line is running for a longer time and now a fault occurs that did not happen before. And we have to set up Innovus in a way that we not only detect the fault via Chameleon, but also be able to identify the kind of fault. Now, that's what I want to show you today. So
you already gave a term out that maybe some of our listeners aren't familiar with. You said the word chameleon. What is that for their reference?
Yeah, this is a software module. Some people call it a kind of artificial intelligence that adapts the software to the current production process and is able to find outliers, is able to find suspect parts.
Okay.
I can show it if I come to our portfolio. We have 3 applications that we cover with SimCenter Innovus. This is end-of-line testing, where we test machinery that makes noise and vibration by itself. The end-of-line test, this could be, for example, an engine, an electric drive unit, an electric motor, transmission, a coffee machine, a washing machine, whatever makes noise. And of course, we have a lot of these applications in automotive industry, but also in white goods, household industry, and industry itself. Yeah, and there we have 2 main goals. One is to sort out items that are suspect in terms of noise and vibration. And we also use noise and vibration to find faults that have influence on the noise and vibration. So an example in what you see in the picture is an gearbox, an automatic gearbox of a passenger car. 2 different general types of faults are possible there. One type is the gearbox makes noise, but it will work for 200,000 miles. This is a typical acoustic problem that we want to find. And the other end, there could also be a small damage of one of the tooth gears that is nearly not audible, but will lead to a breakdown of the gearbox after, let's say, 1,000 miles. So those are the 2 different kinds of faults that we want to find there. And then we also have 2 other applications. One is non-destructive testing. We do a test of items, of parts against cracks, porosity, density, and any other defects that may have influence on the vibration behavior. What we are doing here is, as you may do if you buy some cups in the shop and you want to check if there's a crack inside, maybe you hit on the cup and listen to the sound. If it sounds quite clear, then you know this cup is okay. If it makes a different sound, then there could be a crack inside. And that's the same thing what we are doing here. We excite the part with a hammer, listen to the sound, and if there's a defect inside, we can hear it.
So then we also test sounds like a bunch of ding, 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 and if the frequency shifts, we know the part wasn't made right, huh?
Exactly. Yes, the same as if you would buy a bunch of porcelain for your cupboard at home.
Yeah. So this, I buy champagne glasses all the time, and yeah.
Yes. Okay. Yes, I forgot.
Just right. Yeah. That's my daily drink there. Yeah.
Here in Germany, we buy beer glasses, Yeah, that's by the way, if somebody asks me, is this new what you are doing? I tell them, no, what we are doing, the quality test methods that we use are sometimes thousands of years old. And I'm sure that also the old potters in Egypt did it the same way with their vases. If they want to check if they are okay, they hit it, listen to it. And that's what we are doing today in industry. Yeah, and also for process monitoring, we know that a certain automatic process may, if it does always the same, it sounds always similar. And if something changes in the sound, we know that something happens, that something went wrong, and then we can stop the process, identify the fault, prevent the process from sending out faulty parts. For example, the connection rods that you see here, the joints are fitted together in this machine, and during this fitting process, it could happen that part of the joint breaks, and this noise that occurs in that case is audible, and we can set an alarm in that case. Yeah, that's what our customers are doing with our system technology. And the next slide shows what belongs to the complete system. We usually provide the complete solution that consists of sensors to acquire noise and vibration or additional measures. Then we provide hardware that is modular and that is adapted to the application that you have in terms of number of channels that we have to record. And also excitation hammers for the non-destructive testing is part of our hardware that we deliver. And then, of course, the main intelligence is in the software. The software records the data, analyzes the signals, and at the end calculates some metrics, compares the metrics against limits so that we can identify the faults. And to bring this all in the line up and running, we provide all the deployment service that is necessary to do this. And we are also in a situation that we often have users that are no NVH specialists, and there we also help in our after-sales support to handle the ANOVUS system. Yeah, that's what we provide. And now I want to show you basically what we are doing more or less during technical consulting and commissioning. So that means the steps that you see in the next slides is not the typical way of working or not the typical start of working with the ANOVUS system. If you buy an ANOVUS system at the first time and you handle it at the first time, then you will get it pre-configured. What I show here is how we configure the setup. So if you have an NVH specialist in your plant, this is something that we can train to this person so that you can do the complete setup by yourself to keep the expertise in your plant. Or you get an impression what we are doing if we are talking about commissioning.
So normally people would have this already kind of pre-checked out and it starts detecting faults right away because they would have maybe had us come in and analyze some data. Exactly. But you're going to show how that analysis works. It's like you're giving away this recipe to the secret sauce.
Exactly, yeah. No, it's not a secret in our case. We show our customers what we are doing.
Yeah, it could be they're using it already and they need to adjust it.
Yes, exactly. That could be one of the tasks. So the example that we have here is the test of an electric motor. You see the motor here on the bottom, it's vibrating. So we assume that we can get some information about faults or any discrepancies in this motor by checking the vibration. So we put a sensor on it, a vibration sensor. And then because of this is a rotating machine, we usually acquire also the revolution speed of the motor to be able to synchronize on the speed. That makes it much easier to analyze the data and to calculate reliable metrics. The two signals from the vibration sensor, and this is an industrial accelerometer in our case that can be pushed against the surface of the test item automatically. You do not need the glue or mount the sensor. It is touched against the surface and that's it. And then we have a laser probe to acquire the speed from the shaft. Those two sensors are now connected to our acquisition hardware. Here's the smallest hardware that we provide. It has two signal channels, two tacho channels, and one communication board to be connected to the PC. We connect our acceleration sensor, our tacho sensor to the box, and then the box is connected to the PC where all the ANOVUS software is running on via Ethernet. So that's more or less the measurement system, which can run autonomously and can check the engines or the motors in the line. But at the end, we have an automatic test bench, and so the system is not controlled manually by an operator. The system is controlled by the test bench. So we also have an interface to the test bench software so that the ANOVUS operates fully automatic in the production line.
I have a quick question there, Olaf. Yes. You mentioned the laser and the accelerometer, and I guess you can also use a microphone. But with electric motors, do you sometimes measure the current? Does that tell you something about electric motors?
Yes, we measure the current with two goals. One is if we talk about small electric motors like motors to adjust car seats or motors for windscreen wipers, such things, there we acquire the current to extract the current ripple to get information about the speed. So we replace the laser sensor that you see here by a current probe to get the speed information. But on the other hand, in this current, there's not only information about speed, also information about the quality of the electric motor itself. So by providing the same kind of analysis as we do for the vibration or acoustic signal, we can filter out faults like eccentric rotors or coils that do not have the same strength or magnets that do not have the same parameters. And such things can also be detected by doing the current analysis. But there we use really FFT, order analysis, modulation analysis, all this stuff, and not only measuring the strength of the current or something like that.
Okay. Just like you would measure an FFT on the vibration, you do it on the current fluctuations.
Exactly, yes. Yes, and interesting what you see in the signal. Then now let's have a deeper view in the software. And there, to understand what happens if we set up the system, it's quite interesting to get some information about the philosophy of the software. We designed the software to be operated on the test bench in an automatical way, and we designed it in that way that we can adapt it easily to a new application. We designed the system in a way that we can modify it very flexible only by mouse click. So we can change the behavior of the ANOVUS system completely for the different applications, and we do not need to program any line of code for it. We can do this all by mouse click. And not only we, but also you can do this by mouse click.
For sure, not all of us are coders, so anything to make it easier is great.
Yeah, exactly. That's true. And it's also a kind of quality management thing. We all are ISO 9001 certified, and you know that a quality management system is behind it. And the quality test system is part of this quality management. And so it's quite logical that also the test system itself has to be quality management compliant. And to do this, you have to test the software. You have to do some well-documented unit tests, application tests, and so on and so on. And if you program one unique software for one test bench, then usually such deep tests will not be done. And so the quality of the software that it's used to check the quality sometimes is poorer than the quality itself. And this should not happen. And that's why we designed it in that way. Yeah, remember we have the hardware that produces data or that records the data from the sensors. And the first application that we have to talk about is the ANOVUS signal processing. That's more or less the application that does all the work, that hosts a so-called measurement setup. A measurement setup is a kind of description how the data are recorded, how they are analyzed, and how the metrics are calculated and against what limits they are tested. And this measurement setup is stored in a file. It is called, or it has the extension AMS. Basically, this is an XML file internally, but we do not call it XML. We call it AMS so that we can double click on it and open it in the Explorer and to distinguish between the other file formats. And in this measurement setup, so-called flowlets are used. Those are modules that are connected to each other and that have parameters and inputs and outputs. One of these modules, for example, covers the hardware. Here I can set all the parameters of the recording channels, and this module takes the data from the hardware and puts them into the signal processing. And it also has an interface to a storage, to the disk or network share, where we can store the raw data that we acquire from the hardware together with some meta information in a so-called ASD file. This is a raw signal data file. It's comparable with an ATFX file. In fact, we also can convert them into ATFX quite easily so that you can analyze them, for example, in TestLab directly. And these data also can reload it in the software. And in that case, the software behaves the same as if it would run online. The only difference is that the data are not received by the hardware, but by the file. And not only this module is included, there are many other modules are in such an ANOVUS measurement setup to provide all the analysis that is needed. And there's also one flowlet that produces results. In our case, those are measurement curves or single value metrics or waterfall diagrams or whatever kind of result you could imagine. And these results are stored also in a file. as a so-called AME file, which is again an XML file type. And the data are also provided in the memory of the PC so that other applications can access them.
Flowlet is your secret thing there for not having to program. That's what you just...
Yes,
yeah.
Exactly. The measurements that are built from flowlets. Flowlets are the signal processing modules, and they have inputs, outputs, and parameters.
Yeah, and it can take data from the hardware live or from a pre-recorded signal. If we had a production run that had a bunch of signals from it, it'll
Yes.
calculate metrics and limits and everything, puts everything in this result file. And you can have more than one flowlet because you could be looking for more than one fault at a time. Is that right?
Yes, exactly. You can do any kinds of analysis in parallel. It depends only from the power of the PC where the system is running on. If you have a complex gearbox, for example, with many shafts inside that rotate at different speeds, we can calculate order analysis on 5, 6, 7 shafts in parallel, can do some psychoacoustics in parallel, can calculate frequency analysis, modulation analysis in parallel, so that we calculate a lot of metrics at the end. And also some very special analysis methods are available to detect several typical faults that could happen in our customers' items. And at the end, we get a list of metrics. If one of them is out of limits, then the item is treated as not okay and is inspected, sent to the repair loop, scrapped, or whatever is necessary in the certain case. And the results, I already mentioned it, we transmit them to the test bench via a software that is called Test Bench Connect. So this is the interface to the test bench PLC, which controls the ANOVUS system, starts the measurement, stops the measurement, starts and stops several measurement steps, sets up parameters according to the device that has to be tested, and at the end receives a list of metrics that is transmitted to the test bench and to the quality database so that we can perform the test. And we can use the same data and show them in our ANOVUS Signal Analyzer. That is the third software that is usually installed on the test bench PC. This software also can be configured by mouse click. Here we can add several windows that we call viewers to represent the data that the flowlets in the measurement setup are producing, and we can also put them in a nice setup so that we can have a panel that can be used at the test bench to show the data. But at the end, it is not necessary to have this analyzer running on the test bench. If we have full automatic test bench, sometimes it is not needed that some curves or some metrics are shown, and then we can work completely headless without this analyzer. Since this is the tool with the high sophisticated graphical interface, this is also used for editing AMS files or for other tasks or for doing analysis of mass data and so on. So this is how the typical setup looks like. And what I want to show you now is how to configure especially the signal processing and the signal analyzer. That means how to combine the flowlets to a setup that calculates the right results and how to set up the analyzer in a way that you can see the results.
And you're not sitting in a production plant, right, Olaf? So you're going to show us maybe with the raw signal time data, the ASD files?
Yeah, exactly. I'm in my home office now, and so I can only show you the data from the raw signal file. But at the end, it looks as if the system would run on the line. If I set the playback to real-time simulation, then you see here exactly the same as what you would see if the system would run on the line.
Yeah, I feel like I'm on the line here, testing one unit after another.
Yes, we have a quite good quality. We have tested 11,000 items. The system was running since we had our call today, and in that time it checks 11,000 items, and maybe it's time now to add some faulty parts so that we not only have okay parts here, but also some faults, because they make the life of the quality engineer interesting.
Yeah, a little more interesting,
Yes. So here you see now, for example, a conspicuous part where we already know the fault, and there may occur one sooner or later that we do not know up to now.
And there you're looking at first order and 17.14 order, so like imbalance in a gear.
Exactly. Those are two faults that I already expected that they could happen. The device under test here is a small electric motor connected to a planetary gear set. And those are the things that we expected that they could happen. And we built in these metrics, set some limits. And what you see here on top, this is the so-called chameleon that does the check of the measurement curve. So here we also can see it here. We have our spectrum. Here I have to add the curve that we can see it. Here we are. So the blue line is the current measurement. The red line is the upper limit calculated by Chameleon. And you see here some parts of the blue curve stick out. And that's why Chameleon says, no, this part is not okay. If I would use an okay part, I switch it to maximum speed, then it would look like this. The complete line is below the red curve and we are fine.
Yeah, you said another word for it could be AI, artificial intelligence, but it's looking at a statistical spread of all the data and tells you if the particular unit you're working with is, and it can look at things you didn't define. Here you had first order in 17.14, but you're checking everything anyway, huh?
Exactly. That's the main goal of this tool. We had this also in past. If you look at this order spectrum, it has, let's have a look. I do not have this in mind, but if I look at the order analysis, this line consists of roughly 8,000 single values. And if you set metrics for the known gear defects, bearing defects, whatever you want, then you only pick out a bunch of order lines. So that at the end, only a few % of the complete signal is assessed by typical metrics. And there's a high risk that something happens with the item that we do not know in advance, and that will not be shown in the points of the curve where we look at. And therefore, Chameleon helps us to find also things that we do not have on the radar. That means this is the layout, how this would look like. And I already showed you this is where we want to go to. And now I will show you how we set up the system that we get this configuration. So the first be the creation of a measurement setup. And therefore we start from scratch. I close the setup here.
And that's not a movie running in your PowerPoint. That's the actual software you're working with. Oh, okay.
That's right. This is my PowerPoint, a nice background from my last holiday in Mexico, and my system is running here. So that's really live what you see here. It's not a video, and that's why I can. Okay, what I want to do, I open other viewer settings, the default ones that shows only an empty viewer. So this is where we started from scratch. I will put the slides on again. Here we are, create the measurement setup. At first, of course, if we create a new setup, we have to think about what do we want to do. We have to take into account what sensors do I have, what is the test item that I want to test, what kind of analysis methods do I need, what kind of metrics do I need to test this certain item. This is something that sometimes is defined by the NVH department or by the quality department. Sometimes we define this together with the customer. This has to be clear what is needed at the end. And then if we have defined that, the next step would be to add all the modules that are necessary to provide this functionality. And therefore, we have a certain library of flowlets, which is divided into so-called flowlet groups. They are called physical channels, logical channels, triggers, profiles, and so on. And that's what I want to show you here. For example, for this example test bench, electric motor, one accelerometer, one laser sensor, I could create a small setup. So I would start with the acquisition. This is the flowlet that covers our hardware. I take the SRD Acquis, that is the name of this flowlet or the type of this flowlet, and create a new instance of this flowlet. And you see here, if you open all these tabs, you'll see we have hundreds of these flowlets. Of course, if you want to set up a new measurement setup, then you need to know what every flowlet does. Therefore, we have a nice reference, our flowlet reference, where you can find the information about all the flowlets that are shipped together with the Novus. So
I think I saw that the flowlet document was 367 pages. So there's a lot of flowlets, but they
Yep.
cover everything from gathering the incoming data to the processing to the final analysis. Huh?
Yeah, exactly. Every time we have a short description what is done in the flowlet, then we have a description of the input, the output links, and the description of all the parameters. And they are quite detailed, and we describe usually very deeply what we are doing in this flowlet. So there's no secret in our signal processing. We describe exactly what we are doing. And that's also a question of quality management. You have to document what you do in your quality in terms of quality management, and we help you to document this in that case that we disclose what we are doing. So let's go ahead.
It kind of looks to me like they're laid out in somewhat logical, like starting with acquisition, logic,
Yes.
then triggers, then the analysis or something, huh?
Yes, then after acquisition, we do calibration. That means the acquisition flowlet delivers volt from the sensors and voltage signal, and the calibration flowlet converts this into acceleration into G. Or the tacho acquires pulses, and in the RPM channel, I explain the system how many pulses per revolution I have to calculate. And the trigger, there I have some synchronization flowlet and also a trigger that produces events that we use to calculate reliable data. So that's also very typical for an end-of-line test, that we have to calculate our measurement curves and metrics always under the same conditions. So we have to cut out always the right part of the signal to calculate a certain metric. And cutting out the signal we do by defining triggers. A trigger usually has a start and an end point, and the start point and end point is transmitted with the data stream and can be generated from time, from speed, from external signals. For example, we can provide an RPM trigger. That means we can start the analysis if the device under test starts to turn at 1000 RPM. And then let's assume the motor ramps up to 5000 RPM, then we can stop at 5000 RPM. And we do this exactly always with every measurement at the same point so that we can produce reproducible data. So therefore we use triggers. Then the first simple thing is to show the signals by themselves by using RPM profiles, time signal profiles in our cases. For the speed, the RPM profile. For the acceleration signal, we use a time signal profile. And you see here, these modules are generic. We do not have an acceleration profile or sound pressure profile. This is a signal profile. And what's behind the signal depends from the calibration, and the profile adapts itself to the kind of unit that we measure there. Yeah, and then we start with analysis. In our case, we do a simple order analysis. And from the order analysis, we calculate spectra by using the spectrum averaging flowlet, and we calculate order levels or order metrics by a flowlet called order level ratio. And then I already mentioned it, we want to do a classification using Chameleon, and at the end, we need some results. So now I have, and I have one flowlet I forgot. There's a special flowlet that we use to display some status information on the screen. You remember there was on the screen, there was the RPM running here, and this is something that we can provide by this status flowlet. So now I have all the flowlets on my tables.
And maybe I misspoke before. This is a collection of flowlets, but you would not call this a flowlet, or what's the word for the collection of flowlets?
This is the measurement setup.
Okay, so the AMS
Exactly, yes, the AMS. But it's not only the collection of the flowlets, it's also how they are connected to each other. So you can describe this a bit. I want to do some kind of measurements with real hardware devices on my lab desk. And at first I put all the devices that I need, an oscilloscope, and a counter, and voltmeter, everything that I need I put on the table at first. The difference is in my lab, I only have one oscilloscope. Here I can have 5,000 of them if the PC has enough memory. And then in the next step, I grab a bunch of cables and connect the devices to each other. And that's what we are doing now. You see here on the left side the outputs of the flowlets, on the right side the inputs. And I connect now the first audio channel of my signal recording device with the calibration flowlet. I connect the first tacho channel with the RPM channel. Then I can take I have to add here some links. Then I can add the output of the calibration flowlets with the input of this synchronization flowlet, the tacho here, the RPM, and the signal from the sensor, the tacho from the sensor, I also put on my trigger and so on. And so I can connect all this stuff together so that it makes sense, that I take the signal, calibrate the signal, route the signal through the order analysis. This is something that I can also show you here in the order analysis. I put the audio signal in, the RPM and the tacho, and the output of the order analysis now is connected to, there's my order analysis, here we are, to the spectrum averaging. And now here I made something wrong. Yeah, and so on. There are a lot of wires to connect, but at the end I would need 2 or 3 minutes to do this completely. And at the end we could save our setup and could do the next step with it. So to make it a bit shorter, I already prepared the complete setup that is connected in the right way. And you see I also renamed the flowlets. When I click them together, some generic names have been created from the software, but now I also typed in some names that makes it easier for me to understand what I'm doing here. And so this looks a little bit nicer. And here I can also do the first parameterization. So for example, if I open the recording flowlet, I could set the sample rate that I need. I could activate the signal channels that I need, could activate the ICP power supply for the sensor, set the input gain to a value that makes sense for the application. Also change the name of the channel, accelerometer top, for example. If I have 2 of them, it makes sense to name them in a way that I understand where the signal comes from. And then I also can configure the playback and the saving of the data files. For example, here I can activate the signal saving. I can change the mode, how the files are named. For example, I can use the timestamp to make it easy. Then every file has a different name and I do not have to care about it. I can control when the file will be saved. So if I have a very long measurement, sometimes we have very long measurement cycles of the complete item, I can control that I only want parts of the complete cycle that are interested for me to keep the size of the raw data files in a smaller range. So then I can go through my whole setup and set up the parameters in a way that I think that it fits as a first choice. And then I could save it. In my case, I only close it because I do not remember if I made something wrong. And now I can use this setup and load it in the signal processing application. So I load my setup, webinar test, and now because I have no hardware connected, I can do some offline analysis. So I could do, for example, the analysis of this file. And you see here the progress went from 0 to 100% in a quite short time. Now I have calculated all the measurement curves and metrics from the first file. Yeah. The next step would be to make this visible. It's also quite easy in the Anovis analyzer. I can add a configuration for my results. So if I go to configuration view connection, you get a window that shows all the results that are calculated by the measurement setup. This is now only a quite small list, so to say. If you have a more complex setup like the one for the automatic gearboxes, you have some 100 of these links there available to select them and combine them to each other. But here it's quite easy. I mark them. I let the system automatically generate a viewer configuration. Now I have for all the results that are calculated by Anovis, I have a viewer, and as stupid as Windows is, they are all now sitting here in this viewer window in a not very nice way. And so my next step would be to sort them in a way that it looks nice. For example, I could put my level meter here on top that I see if the signal is overloaded. So this looks like that. You see here a bar graph that shows the level of the signal. And in the next step, I could let the system run a bit. Then we see it online. In the next step, I could show the recording time below this graph in that way. Then the online RPM can be shown here. Also put a window here, and now I see there's a digit behind the dot, which makes no sense for an RPM. It's much too precise. I can define how the RPM should look like here.
Many of our customers, though, all off. They do 2 digits after the test for RPM there.
Okay, yeah, this is much more precise than the sensor is usually, so this would be enough. Yeah, but you can set it however you want.
Pulses per rev encoders, the usual.
Yeah, yes, you're right. Yeah, and then we do the same with the other graphs, and to make it a bit shorter, I can duplicate the position of them. Makes it a bit easier to build this all. Oh no,
And I know you have a German version of the software. If you went back in there, that Schellen means confirm or something?
Yes, this is not my software. This is the Windows.
Your Windows, yeah.
Yes, some of the dialogues are. No, where's my? Here we are.
Coming from Windows.
Are provided by Windows, yes, and they are German.
The English software on an English PC, it would all be in English. But we're learning a little bit of German as we go here.
Yeah, this is what the Windows provides for me. Here in the software, in this version, I have English, Spanish, and German available. And in the next release, the 24 or 6 that will be released in June, we will also have Chinese, French, Japanese, and Korean language available. Okay. So if you have, or Spanish is even still available. So if you may have production plants in Mexico, the colleagues out there can use the software in Spanish language. Yeah, and if I designed the surface in the right way, I press fix, and then I have a panel that can be used on the test bench. I can save these few settings, and now if the next time the system starts up, it will look similar. Yeah, so that's how the software is designed. I also put this together in some bullet points here, creating the fuel configuration. That was the part that we were doing here. And of course, setting parameters. That's something that I did not show in detail because not all of them can be set when I'm in offline mode. For example, setting the gain of the audio channel. This is something very typical for the commissioning, that we do not know in advance how loud a certain item is, how much vibration it creates. So we usually set an arbitrary value, and then if you do the commissioning, we adjust this to the real life. And therefore, we look at the bar level and set the input range in a way that it fits. Or if we want to set the pulses per revolution, usually we get in advance the number of pulses per revolution of the sensor that we have, but then we double check if it fits. Or if you want to calculate an order analysis, then we check if we have chosen the right maximum order, the right resolution, and all the stuff. So all these parameters can be or should be set, and therefore we have to go online if we want to set up the parameters of the recording, but all the other parameters can be adjusted afterwards.
Yeah, there might be parameters you want to adjust for, like the limits to detect a fault, for example. Would
exactly.
that be
Yeah, this could be done later on, and also based on files. So that's also how we often work. We record the data, then we give back the test bench. In the commissioning, it's always hard to get enough test bench time. There are so many people working on the test bench, or so many colleagues working on the test bench, doing parameterization, optimization, and so on. And if you want to block it for 2 or 3 hours, then it's sometimes difficult. And so we only need some minutes to record some data files, and then we can sit on the desk and analyze them. Yeah, and this could look as follows. So for example, I stop this. If I look at the standard mask that we may have on the test bench that looks like this, we already have seen that single step we can detect several faults, like for example this one with the gear mesh. Here we already defined the metric, order number 17. When this is above 120 dB, then we assume that the gear mesh stage has an issue. Here in that case, it's 123.4. That means it's above the limit. And then we also may have another fault like this. Chameleon said, no, this part is not okay, but all my metrics say green. And so this is now the case where I have to analyze the data to find out, is this really a fault that occurred now? Do I have to catch it? Can I identify it? Can I define a metric to identify this fault? Therefore, I can have a first view in the spectrum. I modify the setting of the spectrum a bit, just to 160. Then I activate a so-called tolerance view, where I can see on what points the limit curve is exceeded. You see here, in our case, by the way, I used the mouse wheel here to scroll into the graph on both sides. So it's also very convenient to deal with these data. And now I see here, okay, in case of the faulty item, the order number 5, the order number 10, 15, 20, and so on looks higher than on the other items that have been used to create the tolerance scheme. So I have a raw estimation what could happen, but I want to know a little bit more in detail. And therefore, I add a new window to my viewer configuration.
The order 5 was not a fault you were looking for originally. Order 1 and 17.14 were.
Exactly. Order 5, this is something we found out that is related to the commutator of this electric motor. And so we already found out, okay, this could be an issue in that range. And we found out that some paper was not tightened in the right way and was flapping around the commutator and produces this noise, clack, 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 something like that. And so I add a new viewer to my viewer configuration now. This is a so-called analysis viewer. And here I can use a so-called class editor to inspect many files at the same time. So here I can, for example, load all the production data. Okay, now I added all the curves here. You see a nice scatter of the curves, and I can choose another class to add the faulty items that I'm interested in. Here in our case, those 4 measurements, and we now clearly see, yes, the orders 5, 10, 15, and so on are outside of the limits. I can also inspect them here. You see here the blue class, the red class, there's quite a big difference. But not only at order number 5, also at other orders like the 15 also shows a very big difference. And so I use this to define a new metric. And this is something that I do directly in my setup. Okay, so I already prepared something. It is called motor orders. And here I can set up a so-called harmonic level. That means I take the order number 5 up to order number 35 with a step of 5 orders and sum them together to one metric. And this is what we calculate now in the next step. I activate this metric, and then I do maximum, endless, and no, not endless, one increment automatically. So now I can recalculate all the files, and now I should have a new metric that is called motor orders, harmonic 5 in steps of 5 to order number 35. But you see there's not yet a light behind this motor order, because up to now it does not have a limit. I only calculate the metric, and in the next step I want to know how to set the limit. And therefore
and in that case, it was actually not just a single order like the first order and 17th. It was 5 and its harmonics. That's interesting.
Yes. Yeah, and I'm not really sure if the fault shows a slight different representation, if it will be again order 5, or I assume sometimes it can happen that order 5 distance is too low and I have to look at order 15, and to avoid this, I sum them up all together, and then I'm sure that I catch it, even if it looks a little bit different. So now I added some so-called statistic viewers. I can redo my analysis, delete all classes, add the curves that I'm interested in. So for example, I take now all the measurement curves that I have calculated. I put my new fault. Oh, sorry. I sorted them in the wrong class, so I have to move some of them to class 0 and some of them to class 3. Now we have 3 different, no, class 2 looks better. Move to class 2. And now we have 3 different colors. Blue is production, green are the faults that we already find, and red are the new ones. And we see now the same here in the statistic viewers. Sometimes we have to set the scaling in the right way. And what you see here now is the trend of the measurements that we have with respect to the metric that we have. So here is the same view settings, auto plus level.
So you see a trend, plus you see a histogram on the right there, huh? Of the
Exactly. Right is the histogram, and here you see a trend. Maybe I have to zoom out. However, you see here, if you look at the settings, let's put this to 130 and this to, let's say, 40. You see for the other metrics, for the unbalance and also for the gear metric, there's no difference between motor orders and not motor order issue. But in our motor order flowlet, we see there's a big difference between the good motors and the motors with the gear mesh problem and the motors with the motor problem. And so we can set the limit here at, let's say, 120 to distinguish them from each other. So that's what I will do now. I activate the limit 120 dB. And now I can recalculate all the data. In the meanwhile, I can tighten this a little bit up, put this in the right position so that it looks nice. So I can save my viewer configuration that it does not disappear in case I restart the system. So now I recalculated all the data. I add them again. I have to check that I'm in the right folder. Okay, here we are. Then I put them to get the same colors to the right classes. And now we can have a look again at the representation of the data. Here it looks, this is the gear mesh metric. Only the files with gear mesh issue are outside of the limits. Then we have the motor orders here, the same for the files with the motor, and the unbalance is no problem at all files. So now we see that we have a new metric which is reliable, where we have a big difference between good and bad, where we can clearly set a limit. And if you do an online calculation, now we can use this new metric online. So single step. Okay, okay, okay. Once again, okay. First fault, second fault. So yeah, that's the way in very fast forward to show what we are doing in commissioning of an Anovis system, or what you can do if you want to set up the system for a new application. And in the second step, I showed you how a test engineer could deal with the system, do some statistics, do some analysis, and generate new metrics in case of a chameleon detected a new kind of fault. Yeah.
Great. Well, thank you very much, Olaf. You really went through a lot, actually, very fast there, and developed even a new metric right on the spot. That was impressive. And I guess that concludes our webinar.
I want to thank everyone for attending. Thank you very much, Olaf, and everyone have a great day.
Thank you. Same to you.